All right, folks, welcome to the sixth session of the workshop. Today, we are going to continue our discussion on classifiers. We are going to cover the loss function for classifiers. If you remember, we have covered the loss function for regression, but we haven't covered the loss function for classifier. It turns out the loss function for classifier takes a little bit more mathematical machinery to understand, and we are going to build that machinery from scratch. We'll reason our way through it today. The other thing that comes with classifiers is, what are the model metrics? How would you know that your classifier model is good? For regression, you remember that we built a model, and then some preliminary measures were just quickly look at the R squared, look at the mean squared error or sum squared error, root mean squared error, whatever, some flavor of it. Look at that, a mean absolute error. And there were a few metrics you would look at. And then you would look at the residual analysis to see if the residual errors, they show homoscedasticity and lack of pattern. If they do show homoscedasticity and lack of pattern, then you feel good about it. You feel, okay, you're moving in the right direction. And then you finally, if you're in lower dimensional space, you plot your model predictions over the data, and you see how good your model predictions are over the data. And for higher dimensions in one of the subsequent labs, and I think in one last lab, I did introduce the partial dependency plots. We also learned about something called feature importance. How much does each feature contribute to the prediction, or is relevant? How much does it matter? So those were the things we learned in the past. But for classifier, we need to learn similar or equivalent things now. Right? So that is the context for today. So the theory today is the review of last week's topics. Then I promised you that I'll make you friends with Emily. So that's there for today. We'll do cross entropy loss function. We'll do model metrics and discriminant analysis. Now, guys, some of these topics are topics that you may have encountered. Almost all of you have taken some online course or are in some degree program or have been taking Udemy, Coursera. Most of you have taken Andrew Ng's class or some other such good courses. So you may have some background, but we will assume no background, and we will develop the theory from absolute scratch for all of them. What are the labs that we are going to do today? The labs we will do today is the California housing dataset, which is a spillover from regression. Then we'll do three labs, three specific synthetic datasets that I created for classification. And those are classifiers 1, 2, and 3. We will do that. So that is our scope for today. So with that there, let's now go to my OneNote writing stuff. I'm now about to get started. I'm searching for my OneNote on the desktop. There we go. So let us say what we did the last time. Sorry. What we did last time was, how did we end up here? Okay, a coefficient of determination. Let's go to the very end. Yeah. This looks like it. So if you remember, we talked about a distance function. And I'll start the discussion here. For linear classifiers, the most relevant, the decision boundary. What are linear classifiers? It is those classifiers that tend to build a hyperplane decision boundary. Right? Intuitively think of as line, and now from there generalize to higher dimensions. When you do generalize to higher dimensions, it becomes a hyperplane. So if you do have a hyperplane, one way, an elegant way to define any hyperplane in any dimension is to think of the unit orthonormal vector. If you can quantify, if you can have the unit orthonormal vector, which I'm representing here as beta hat, then what happens? With that in place, you can have, the tilt of the plane. is well established in the feature space or in your space. The only question therefore that remains is there are still infinitely many planes that you can draw at that particular tilt in the hyperplane. You can fix to one particular hyperplane by now picking a certain distance from the origin of the feature space, of the Cartesian feature space, whatever it is. And once you get the origin, you can then make progress. So that is the distance t here. I mentioned it as t here. And so from that, we went through a little bit of geometric argument to say that if we know the beta naught, and if we know the x vector, the position vector of any point in the feature space, then it is pretty straightforward. All we need to do is remember that this is your beta naught direction, and this is your vector x direction. So this distance dx is basically this from here to here, this distance, like the entire vector. If I do, the total vector is this x dot beta naught is the full base of that triangle. If you look at this particular triangle, a triangle that starts from O, A, and X, O, A, X triangle. If you look at it, then x dot beta hat is the base, is the base of the triangle. I hope you can see that, of the right triangle. Bante, please go ahead. Beta hat is the unit vector orthonormal to the plane, perpendicular to the plane. It is this vector. Imagine this, you have this line, the vector that is perpendicular to the line, right? And now generalize it to higher dimension and think of hyperplanes. The unit vector that's perpendicular, the word you generally generalize this to orthonormal, something that is orthonormal to the plane. Are we together? Yeah. So you take that vector and you would agree that if you look at the triangle OAX and the OAX triangle, right? So maybe I can color it with this little line here. This triangle, if you look at this triangle, if this is X, and you would agree that the base of the triangle is X dot beta hat. Is that straightforward? Right? It's pretty obvious from there. So now with that thing there, now let me see if I can. Yeah.
This precision boundary, when you say the hyperplane, right?
Yeah.
Do we assume that this plane is like kind of a sheet of glass, which is like straight?
Yes, absolutely. No bends. The nature of a plane is it has a single orthonormal vector which doesn't change.
Okay.
Right? No change in the perpendicular vector, orthonormal vector anywhere.
So are there planes where they have bends?
No, you don't call them planes. You just call them hypersurfaces.
Hypersurface, okay.
That is it, but not a plane. You wouldn't use the word plane for that, right? Okay. So with that, so this is it, guys. And so this triangle, the geometry is, when you look at it from a geometric perspective, all of these ideas that go into machine learning, they become very, very straightforward and easy to understand. So let's keep to that. Then, if this relationship holds, then it follows that through a very simple set of steps that we can write a dx as this minus t, and then you can follow the convention, define beta naught as this. And so you come to this lovely realization that the distance from the decision boundary is this.
The screen does not follow your mouse, and there's no mouse on the screen share.
There is no mouse on the screen share. Huh? Okay, let me find a way to fix it. I wonder how to do that. Does anyone know in Zoom how to force the mouse to show? I don't know, unfortunately. But how about this? I'll take it as a homework. I'll figure out some way. Right? So if I just tap here, then is the mouse visible?
Yes.
Okay, I'll try to tap and bring the mouse close to that. So we have this equation at the bottom left, and I'll also give the location now, bottom left, which just says this is the distance from the decision boundary. This distance, people often in literature also write it as Zx, or quite often just Z, right? So you will find these abbreviations, common notations in the ML literature. So watch out for that. Huh? These are common things. And once you do that, then you realize that suppose we are talking about cherry. Cherry is your positive case. You have a question?
Yeah, I was gonna, so the we don't need to hyper.
Those are parameters, not hyperparameters. They are parameters of your hypothesis. Remember, those are learnable parameters. That which you can learn are parameters. Those which you can't learn directly while through gradient descent are your hyperparameters.
Then are they just future?
Excuse me?
So the betas are just future.
They are just no, they are the weights of the features. They are the parameters associated with the features. The features are x1 and x2, right? All right. So through a chain of reasoning, we came to this realization that this is given by that. How did we, by this very complicated, what looks like a transcendental function, and where in the world did this transcendental function come from? So there's a bit of history to it. It belongs to a class of functions called sigmoid. And I gave a homework to find sigmoids. Can somebody tell me what sigmoids you found besides the logistic?
Arctangent.
Excellent, arctangent.
And
Tan H is another, very much used in deep learning. Anything else?
Error function.
Error function, very good. ERRF is an interesting function. It is actually the integral of the Gaussian up to, so what is the Gaussian? 2 pi. If you're looking at a normalized curve, then it is e to the minus x square. Let me just say t e to the, let me take a dummy variable t square dt from minus infinity to x. This is the error function. And it turns out that this integral, like most integrals in real life, you cannot solve for. There is no analytical or closed form solution to this. So you just leave it at that, and whenever needed, you compute it numerically. So obviously, it's a little bit hard to deal with this. But the beauty of this error function is at least its derivative is easy. What would be the derivative of the error function? It would be the normal function itself. It would be the Gaussian function itself. It would be this, right? So if you do derivative of error function, let me, at the bottom of that screen I am. If you see error function, derivative of the error function, ddx, it will of course be, what will it be? It would be nothing but back to your error function, 1 over 2 pi. Right. We know it's derivative, but we can't solve for the integral in full form. So there are many beautiful sigmoid functions that you can think of. And I said sigmoid functions matter. And the reasoning that we have to get to a sigmoid was, I remember the odds and log odds. How do you squash something? See, the distance goes from minus infinity to plus infinity, right? And with x, the distance increases. Let's say that the distance is something like this, right? How do you squash it to a narrow band? So how do you take this tail sort of, this is one very rough hand waving argument. How do you do that? So you use a squashing function. And so you can think of sigmoids as squashing functions. They squash this thing into an S shape. Are you seeing the intuition, guys? Huh? So this is what we covered. That's a review for last time. So this is all very good. Now we know. So to summarize, what we have is given, I suppose, given, let me use the white marker here, given blueberries, once again, and I won't draw so many of them this time because I hope you remember, and cherries, let's say that these are your cherries, right? You know that you want to draw a decision boundary, which you want to draw like this. This is your decision boundary. And so there is a distance function dx, and based on the distance function, there is a probability function, which is you have a probability function, which basically says probability of x being of a cherry. You can pick something, either blueberry or cherry. Let's say cherry. Probability of a cherry at the point x, given the point x, is equal to, it is the squashing of the distance function, right? 1 plus e to the minus d dx. Do you remember this, guys? Huh? This is where we stopped last time. Now the question is, this is a probability. How do we learn these parameters of d? D ultimately is made up of right? So what happens? We have a beta vector, which is made up of beta naught, beta 1, beta 2. We need to learn these parameters. So what is the path we take to learn the parameters? If you recall, how do we learn the parameters, guys?
Gradient descent.
We use gradient descent. Our big magic is we need to do gradient descent. So now let's try to connect the dots. We know that we need a loss function, and then the problem is essentially solved, because the moment you have a loss function, you can gradient descent. Are we together? Right? And by now, yeah, you have become good at gradient descent. We can gradient descent. The question is, what is an appropriate loss function? So let us reason our way through and see what could be. Suppose we take the positive case. Let the positive case, let us say that you have some measurements, some measurement x1, x2, and then you get, the y, actual y, right? The x1, x2, and actual y. And so let us say that you have some specific value. Pick any point. Let's say 2, a point, and 3. The coordinates of a point is 2 and 3. And it could be, of course, floating point, need not be integer. And y is cherry. So let's just decide that we will mark cherry as 1. What is the probability of the probability of py? The actual probability of a cherry is 1, isn't it? Let's say that it is a cherry. So then there is no doubt about it. In reality, there is no doubt. We know that at point 2 and 3, there is a cherry. That's what the data is. The question is, what is, so this is a fact. Let me just, even though it is a probability of cherry, I'll just write it as, but I'll put it in quotes, because most people in the literature, they just write y. What is the y value? But it is actually the probability of that particular thing, which is a guaranteed probability, a certainty rather, not a probability, but a certainty that it is 1, right? Now, what are we looking at? We are searching, we always will make a prediction. Our y hat is the probability of it being a cherry at point x, of being a cherry at point x, right? Which we will just, as we say, there's a sloppiness of notation, and we'll just mark it as probability at that particular x. Let us say that you use a sigmoid function. You just start by taking random values. Start with random guess for beta. Just take some random values for beta naught, beta 1, beta 2, and you did that. And happen chance, your prediction says that this is equal to, let's say that it says, pick a number, guys, between 0 and 1. Anything. Anybody?
0.45.
0.45. All right. So we will take that. Suppose you get 0.45, right? Now, and then there is some other point, let's say 1, 0.7. And here, the actual predicted value turns out to be, this happens to be blueberry, 0. So probability of its being cherry is actually 0, or rather y is 0. And your prediction happens to be, let me just say 0 point, probability that it's a cherry is, let's say it's 0.7, right? Now, and let me take another point, just for the sake of argument. Let me just take 4, 5. We know that it is actually cherry, and our prediction says that this is 0.9. And then there is another point, let's say, let's take another point, 0.5, 0.5. And this we happen to know is a blueberry, not a cherry. And our machine is telling us that the probability that it is a cherry is 0.2, right? So now if I look at the 4 cases, let's look at these 4 cases, 4 data points, and see how we can think about and reconstruct some sort of a loss function for it. How are we doing with, how good is our prediction for A, guys? How are we doing for A? Say that?
Not so good.
Not so good.
Not good. Not so good. What about our predictions for B?
Pretty bad.
Again,
Bad. It's actually worse. Pretty bad. And what about C?
pretty good.
Pretty okay.
Yeah, it's good. And what about D?
It's good
Kind
too.
of okay.
D is good, right? Because 0 and 0.2 are pretty close, right? So good, you would say good, right? And how do you do good? You are basically looking at, you're comparing these 2 things, how close they are, isn't it? So your first temptation may be, hey, why not look at y minus y hat? Can that be the appropriate measure of doing it? Can I just use the square of this for the analysis? It turns out, for a variety of reasons, and the typical reason people give is that if you use the sum squared error, you will end up with a model where probabilities don't just stay between 0 and 1, it will predict numbers bigger than 1 and smaller than 0 sometimes. So that, of course, is not a nice thing when your probabilities are beyond the definition of probability itself, isn't it? And it has very natural consequences. So that is often a reason given. I would actually not reason it like that. I'll reason it in a more formal way, or sort of what I think is a more appropriate explanation, mathematical explanation, why you don't do this. Right? You don't do that. But what is it that you do? I will give a mathematical explanation, but before I do it, see this magic, and I will just keep it. If I multiply these 2 things, this is 0, right? So you realize that for positive cases, I could just see how off we are. If my prediction is good, actually, let me not bring that reasoning because that will bring 1 minus, etc., etc., and I'll bring that in a separate way. So let's go through the reasoning part of it. See, guys, now let me talk about MLA, right? So I always think of this MLA, but it's MLE. What is that? Let me introduce this with a simple example. How many of you here are familiar with MLE argument in the mathematical sense? Like, if everybody knows where I'm going, I will rather skip it. But in this class, anybody who's familiar with the MLE argument? No, you are. Like,
Maximum likely estimation.
Can you explain it in full detail?
So it is like, I think it's trying to look at the distribution and trying to see, like, with every combination, which gives me the maximum likelihood of, like, the sigmoid function.
Okay.
It tries to look at, like, all the combinations and
Yes.
shift it by like a value and then
Yes. Yeah.
do the
That's pretty good.
sigmoid again to
Yeah.
get the maximum value.
Okay. That's good. Anyone else? Otherwise, okay. Okay, I'll just assume that you'll all benefit. Therefore, for those of you who know, it may be a review. I apologize, but for the rest of you, I'll introduce you from scratch. So I'll take this question. Suppose you and your friend disagree. You have heard of a city called Seattle, right? One of you believes that Seattle is a rainy place. Another believes Seattle is not rainy, right? So is a desert, right? Now, only one of you could be more right in view of data. How would you know who is right? Well, you never know, right? There's always all you can say is with a certain degree of confidence, one hypothesis is better than the other hypothesis, given a data. So let's pose this question, two hypotheses. Let me pose it as two hypotheses. Right. And folks, guys, try to reason. These things are actually very common sense things. Math is, in many ways, the easiest subject to learn, because once you get to the examples, it becomes all looks very easy. Two hypotheses. Let's say, let's take two names, right? Let us say we will take two names, Ram and Shyam. Shyam believes Seattle is a rainy place. And Shyam believes that Seattle is a desert, mostly. So on a given day, hypothesis of Ram says the probability of rain is, let's take a number, a high number. Believes that Seattle almost every day rains. So let's say that believes that there is a 90% chance of rain, right? On the other end, the hypothesis of Shyam says the probability of rain in Seattle is like 0.1. Are we together? It's a very small probability that it's going to rain in Seattle because it's a desert, right? And so now let us see a data, what it will favor. Suppose you have the data. Data is this. On day 1, 2, 3. Let's take day 4, just 4 days. The first day it rains, rain, no rain, rain, rain. 3 days it rained, right? So according to Ram, let's see what is according to Ram. See, each day is an independent event. In reality, it's not like that. But if it rains today, the probability that it will rain tomorrow is quite high. There's sort of auto regression in the data. Right? But we'll forget that. Imagine that each day is separate in a very simplified weather model. And so if these are independent assumptions, so let me put this caveat. If we take the simplistic belief that rain on one day does not affect rain the next day. Suppose you take this belief. So you would say, oh, according to Ram, let's say Ram, the probability of rain was 0. So it is all we need to look at is he got the event that happened is it did rain. Probability of no rain, probability of rain, probability of rain. Isn't it? Because the hypothesis says that no rain. So we have to take 0.9 times 0.1 times 0.9 times 0.9. Are we together? Does this make sense, guys? Right. So that is equal to, and that is equal to, let us say, 729. Is that correct? 81. Yeah, 729 into 10 to the minus 3. Right. And according the probability of rain, according to Shyam, it was no rain. What was the chance of no rain? This. And the chance of, chance, again, the same thing. But what is the probability of rain according to Shyam? The same thing. When you do it for Shyam, how much does it work out to be? According to Shyam, 0.1 times 0.9, just the opposite, 0.1, 0.1. What does that come to? Would you agree that it comes to
10 to the power minus 4, I think.
minus 4? I apologize. Minus 4. Yeah, there are 4 terms here. You're right. So each term brings 10 to the minus 1. Good. So 10 to the minus 1. Good catch. So now you realize, so it turns out that we just look at that. If 2 things are independent, if 2 events are independent, and both of them happen, the probability of its happening is the product of the individual probabilities, isn't it? You remember that we learned in basic things that suppose you have event A, event B, and then the joint probability of AB is assuming independent events, probability of A times probability of B, isn't it? So generalize from that, if 4 days it rains, right? What happens according to this? We could have taken only 2 days to prove our argument, but I just took 4 because 2 looks too little data. Is the joint probability according to Ram of rain is 729, right? Into 10 to the minus 4 of this seeing this event. And according to Shyam, the chances of seeing this event is far, far less. But this event is there. It's a fact. So which hypothesis makes this event, now listen to the way I'm saying it, which hypothesis makes this, the data, this event that has actually happened, the joint event of rain and 3 days rain, 1 day no rain, which hypothesis favors the data? Or the data favors which hypothesis? Either way.
Shyam's hypothesis.
No, Ram's.
Ram's hypothesis, right? Ram's hypothesis, by Ram's hypothesis, you're far more likely to get the pattern than according to Shyam's hypothesis. In other words, by Ram's hypothesis, you're far more likely to see 3 days of rain and 1 of not. By Shyam's hypothesis, you shouldn't be seeing anything like that. You should be seeing mostly dry spells and maybe a day of rain. Does this make sense, guys? So which of the hypotheses would you choose? If you have to say, this is the data, who is more likely to be right?
I'm getting confused here. Like, see, rain,
You look
3
at the
days of
data, There's
rain.
3 days of rain and 1 day with no rain. So just
How
looking
did
at
you
the
get?
data, looks rainy.
How did you get Shyam's more than Ram's?
Shyam is not more than Ram. Shyam is far less than Ram. Shyam is only 9 into 10 to the minus 4, and Ram is 729 into 10
Oh
to the
yeah, sorry. Not 9. Okay, sorry.
So,
I didn't realize. Yeah, sorry.
So what we are essentially, that the probability that we written down there, right? 729 into 10 to the power of minus 4
yeah.
is essentially the probability of a compound event.
Yes.
A compound event being
Yeah.
rain on the first day, no rain on the second day, rain on the third day, and and rain on the fourth day. It's a compound event exactly said like that.
Exactly.
We cannot summarize it as a compound event, which is rain on 1 day and rain on 3 days and no rain on 1 day. That's a different event, which we need to do a little more arithmetic to get to that event.
No. See,
Took a
because
simple
these days are
caveat.
independent, even if you rearrange it, it doesn't matter. The fact of the matter is 3 days it rained, 1 day it didn't.
But then we'll have to add the combination term as well.
Combinations also, Asif.
Yeah.
Yeah. You could see when you do the joint probability, the likelihood that It is like that. At this moment, I've taken it separately up to some factor. Okay.
Okay.
It doesn't matter. But would you agree that the same, see, whatever, same factor will be true for Shyam also. So barring all this 10 to the minus 4 and some factors here and there, you agree that this Ram's hypothesis says it is far likelier to rain than Shyam's hypothesis, isn't it? Data favors whose hypothesis?
Ram.
Ram.
hypothesis.
So we could alternatively make it, you all deal with it in real life experience. So let's say that there is some airline, like some new airline that comes through, right? Let's call it, I don't know, Goose Airline, right? So in the Goose Airline, your hypothesis is it's always late. Another person's hypothesis is it's always right. Whose hypothesis would be correct? All you need to do is wait and see the data, how many times it's on time and how many times it's late. The data will favor somebody's hypothesis, isn't it? So one way to know whose go ahead. Yes.
So when you came with the hypothesis, you said Ram's hypothesis is 0.9 probability of rain, and Shyam's is saying 0.1.
Yeah.
Is the sum of that has to be 1 or?
No. I could have done anything. It need not. Actually, since you said I took an unfortunate number, let's make it 0.2. So now 9, 8, 72. So now, okay, they do not have to add up to 1. So 72. So you realize that still Ram's this product, the probability of this joint event is 10 times more than 10 times more than Shyam's probability, isn't it? So they,
No.
and there's a 0.9 also sitting in between. Oh, sorry. Yes, you are right. Oh, yes, of course, the converse. Nice catch. So yeah, so I'll give it to you. So it's just 64. Let's say, very good, 64. I hope it's 64. Yeah, 64, right? So this is a good catch, guys. Huh? So the point that I'm trying to make is that who would you believe in view of this data? Ram. So what you say is that the joint probability of the data being there, data being true, given a hypothesis. So pay attention to the wording that I'm using. The joint probability of the data happening given a hypothesis H, right, is basic. This is what it is, right? Are we together? When I multiply those probabilities, I have some hypothesis. A hypothesis will have some probability of the individual events. Given a hypothesis, given, the most important word is given a hypothesis. This particular thing has a name. It is likelihood. It is the likelihood of this data given this hypothesis. Are we together? Remember, it is not probability. It is hypothesis. That's why, what am I saying? It is not probability. It is likelihood. So far true? Right? And this is a very crucial concept, folks. Most people, it's a very elementary thing, but probability is something where we all tend to stumble on elementary stuff in real life. A probabilities of something happening and not happening adds up to 1. Likelihoods, on the other hand, there is no such thing. It doesn't behave like probability. It is just a joint probability conditional on a hypothesis. Right? So can I just call it? Likelihood is, in some sense, likelihood is the probability of data conditioned on a hypothesis. So without a hypothesis, there is no likelihood, right?
So if there is no bound likelihood, then how do you compare?
We'll come to that. We'll come to that. And it goes into the very lovely thing. You may vaguely remember, if you took the math course, is that bias box,
Yes.
the toolbox. So that's beautiful. I won't cover that because today is just classifiers. And I want to keep the discussion fairly elementary. So guys, this is important to remember. Likelihood is associated, likelihood of the data given a hypothesis, right? But how are hypotheses in regression and classification given? In the case of linear regression and logistic regression, our hypothesis is parameterized by beta 1, beta 2, beta 3, etc., right? The betas, isn't it? Right? Now in the case, so now let's go here and I'll show you some interesting magic. This reasoning, guys, is foundational to machine learning. So pay attention to it. Let's go back to linear regression. For linear regression, what happens is that you predict the data is y is equal to beta naught plus beta 1 x plus beta 2 x2, so forth, isn't it? On the other hand, in classification, in logistic regression, classifier, probability of a given class, let's say cherry, given x, so y is a function of x, is equal to, let's say, 1 plus e to the minus z, right? And it belongs to the set of 0 to 1. It only goes from 0 to 1, right? So these are the two realities. Now, see what we say. And it's quite interesting. We say that suppose you fix your betas, you have fixed probability of x. Remember, it is based, this is what? Z is equal to beta naught plus beta 1 x1 plus beta 2 x2 in our example, right? So basically the probability is parameterized by the betas. I hope I'm making an obvious statement. So now comes this question. Suppose two different people have two different hypotheses. In this classification setting, two people, Ram has a hypothesis Ram, a set of theta, let me just call it theta actually, not theta, beta, because your textbook uses beta, has a hypothesis B, right? Which is this beta naught, beta 1, beta 2 associated with Ram. Right? And let's say that there is another hypothesis. These are two different friends and they have completely different hypotheses, right? Shyam. Right. So for example, in the hypothesis plane, this may be Ram, right? And this may be Shyam. Oops, sorry. I apologize. And this may be Shyam. Shyam's hypothesis, right? For the same data, there's some blueberries here, and there is some red berries. There's some cherries here and there, right? For the same data, there are two different hypotheses of the decision boundary, right? Now the question is, who is right? And how do we, who is more likely to be right? Which of the two hypotheses is more likely to be right in view of the data? When you visually look at the data, it's clear that Ram is doing better, isn't it?
Yes, sir.
But how do we now quantify it, bring it down? So let's ask this question. For every point that Ram gets right, so Ram says that at every point, there's a probability that something is a cherry, right? So let's say that we have a table. Let's go back to our table of data. There is x1, x2, the ground truth, y is equal to 1 means it's a cherry, y is equal to 1 cherry. Right? It's a ground truth. And again, it's a bit of an abuse of notation. What you should really say is the data says that the probability of a cherry is 1 because it is a cherry, right? And then you have your y hat. Y hat is equal to probability of x, right? Probability of it being a cherry. So let us say that you have a data point, something, 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 something. It is a cherry, and you come up with some answer. Let me just call it, this is your first data point. It's a probability of this. Let me just call this. At the first point, it is this. It is really a cherry. Something, 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 something. Let's say the second point also is a cherry. Right? So, let me map it somewhat to your weather example. Rain, didn't rain, 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 or something like that. Well, okay, I'll mix up the order. Something else. And it turns out that it was not a, it was actually not a cherry, but ultimately what prediction model tells you is probability of a cherry, right? So third probability of a cherry, and fourth is also a cherry, four cherry. And let's say that the fifth is not a cherry, probability of this. So now let's reason through and see how we will somehow create a likelihood. What is the likelihood of Ram's hypothesis versus Shyam's hypothesis or any other hypothesis? So you would say that, see, the hypothesis has the parameters built in, right? So now I'll just change the notation to a little bit more exact. I would say that probability that it is a cherry given, probability of a cherry given, well, people say theta, sorry, I'm used to writing theta, but your textbook writes beta. Given the hypothesis, each of them have their own hypothesis. Ram has the hypothesis of beta, has a preferred set of values for the beta, and Shyam has a set of preferred values for the beta. Each of them is their individual hypothesis. Would you agree that the joint likelihood of seeing this event is like this? Probability of seeing it is P1, and if you don't mind, x beta, I'll just remove it. A probability of again seeing it is x beta. Now, if there's something very interesting, you have the likelihood when you don't see something happening. What should you take? The probability, you have to look at the probability of it's not happening. The model is telling you the probability of it's happening. But when it doesn't rain or when it is not a cherry, what do you need to look at? Probability of it not being a cherry, which would be 1 minus probability of 2, 3 x beta, because it didn't happen. It wasn't a cherry, isn't it? Just as we said, probability of not raining is the 1 minus that. And then we look at probability of this. Probability of the fourth data point, x beta, right? Actually, if it is with a little bit of abuse of notation, let me just remove this subscript from here. It's more meaningful for me to say x1, x2, and remember that x3, x4. I'm not looking at the components of the vector. I'm just looking which data instance it is. And the subscript here is, here refers to the specific data, specific datum, right? First row, second row, third, fourth row of data, right? So if datum, let me write the word properly, specific datum. Now, this is what our probability is. Would you agree? Now, the only thing is, this thing is called the likelihood. The likelihood given, what is the likelihood dependent on? Data is there. You can't fudge with the data. When you are learning, see, think about it this way. When you are trying to learn, what is it that you can play around with? The hypothesis. You're jumping all over the hypothesis space, finding, okay, where is the likelihood going to be better? Isn't it? So given the data, assuming that the data is a ground truth, The only knob that you have to turn are the betas, isn't it? Good. Right? So beta, and that's why you often see that it is referred to as beta or just beta, or it is also referred to as a beta given the data. Right. By the way, I'm using the scripted D through all the quizzes. By now, you must have noticed that I refer to the data, the set of the entire data, as D. D being is the data set. Think of it as the ground truth. Given the ground truth, now likelihood is a function of beta, given the ground truth. This vertical line, always say in your mind, given as, given data, what is the likelihood of beta? So now whose likelihood is true? All we have to do is plug in the probabilities, isn't it? We just plug in their probabilities and see which one is true. So now whichever hypothesis maximizes this likelihood, would you agree that that hypothesis is the best we can have? We now will worry about how to learn that hypothesis, but let us at least agree on the truth that we now have, we are very close to quantifying the error. We say, hey, you know what? I know one way to give the error is, or when close, very close to it, we still have to go a little bit of a journey, but likelihood is a pretty good way. I need that hypothesis that maximizes the likelihood of what I am seeing, that it's been raining 3 days and not one, and dry one day, or in the case of cherries and blueberries, that these many times, these points happen to be cherries, these points happen to be blueberries. So far, so good, guys?
So
Yes.
the data that you do, say suppose that the original data you have, the test and the train, I don't want to confuse, but then you will always, the train data has to be constant across both the guys, right?
Yeah, they both are looking at the same data. So yeah, they have to. So just like in the case of rain, the reality is 3 days it rained, 1 day it didn't. Right. That's a reality staring both Ram and Shyam in the face. Right? In the same way.
Pick some part of the data and
No.
say my hypothesis.
No. No, then you become a politician.
He's right. But otherwise you have to make sure that
yes.
both you apply the hypothesis
yes.
to the same data.
Yes.
Data remains constant.
That's right. That is true. That is it. So now, given the whole data set, and see, you actually asked a very good question. What Sachin asked is that, will these two, Ram and Shyam, see the same data? The answer is yes, the same training data. Not only that, in the training data, remember, the magical word IID must remain true. Do you remember what IID is? Pradeep? You go ahead.
Identical data.
Independent and identically distributed. What it means is that independent means because I took this data, it shouldn't affect the next data, right? So like a toss of a coin is really independent. You toss a coin, it doesn't matter what was the result before. Next result is exactly the same, right? So in other words, data are not, one is not affecting the other. And identically distributed means that they are taken from the same ground truth. One rough way of saying it, they represent the same reality. It shouldn't be that one guy's data, like see, for example, if you pick one data from Arizona and one data from Seattle, and you want to make a prediction about Seattle, it would be unfair. You have contaminated it. Means the distribution of the probability distribution of rain in a more formal language in Arizona is different from the probability distribution of rain in Seattle. Now, more simply put, that is a different reality from this. So I can't mix the two up. IID. That's what IID stands for. So they all have to be the same. Okay, so guys, now we are coming to the end of a very interesting intellectual journey. We all realize that there is such a thing as a joint probability given a hypothesis. Right? The joint probability of this data happening at all, given this hypothesis. And that joint probability is called the likelihood. The likelihood is a function, given a ground reality, given the data, likelihood is simply a function of the hypothesis that you pick or of the parameters, therefore, parameters. And so which hypothesis would you pick? That hypothesis that maximizes likelihood, isn't it? So common sense says, and this is a big truth we will stop at, a big realization that we will stop at, it represents, and then I'll take questions. Huh? So we realize that common sense says, well, I say common sense. Later on, I'm going to revise that. Huh? The Bayesian way of looking at things is slightly different, right? We will revise that. But let's say common sense in code says that pick the hypothesis that maximizes L beta, given the data set. Right? Or in your book, it just refers to L beta, right? Probability of that hypothesis, beta, right? So more formal languages, what is the arg max? What is the beta star that maximizes the probability? What is that hypothesis? What's the value of the beta that maximizes this given the data set? This is our main goal. We want this. Now, from this, we are very close, inches away from creating a loss function. Yeah. Are we together? We'll see how to do that in a little bit. Your question.
So on the data, we are assuming that it is like kind of balanced, right? And what if the data is unbalanced?
This is still true. Invariant of that. Invariant of that.
But if you have like lesser sample structure in a 4 out of 2, and then in that case, the probability is higher on the
No. Probability is not a proportion of blueberry or this. See, what you're talking about is, yes, you're talking about an important